Hey everyone, this is the first of probably two or three videos where I show you how we arrive at the kinematics equations. So in physics, deriving an equation can be an important way to see how all the physics connects together. And so that's the point of these videos right now. These are not mandatory viewing for success in physics, but they can be very helpful in showing you what the physics is all about. So I'm going to pick the first and the fourth equation to show you and use this velocity versus time graph to show you where these equations come from. So the first one's pretty easy. So this is a graph of velocity in the x direction versus time, and we're going to imagine that we are going to stop analysis at some time t, and then at that moment, there's a certain x velocity. And so it's important to remember that this variable vx naught is the initial velocity in the x direction. And so I can label the y-intercept as vx naught. And so this one comes basically directly from the graph itself. And the idea of the definition of acceleration plays a part. So there's actually two ways to derive this. The first one is algebraically, to say that acceleration is the change in velocity over the time. And if I multiply both sides by t, I get a change in velocity is equal to acceleration times time. Now, delta means change in. I don't have to really do anything with the time, but what I can do with the velocity is say that the change in velocity is v minus v naught, and that's equal to a times delta t. And so a quick rearrangement of this, I get v equals v naught plus a times time. And then I can put in my x subscripts if it's in the x direction, or the y subscripts if it's in the y direction. So that's just one way to do it. The other way that I like a little bit more is to just look at the line and what we know about physics already. This is a straight line, so it has the format y equals mx plus b. One of the things I'm going to ask you to do a lot during the year is replace variables that you know from algebra with physics variables. And so if I take a look at this graph, the y-axis is the x velocity. So I can replace the y with vx. The slope is the one physics concept you need to bring to this problem to understand it. And the slope of a line on a velocity versus time graph is equal to the acceleration. And I'm realizing I forgot the x there. So the m, the slope, is the acceleration in the x direction. The x variable is time. And then the b, that would be the y-intercept, is our initial x velocity. And so vx naught. And so just take a look. I'm not going to rewrite it, but this equation is just a rearranged version of this equation. So that's the first equation, and that's probably the easiest one to show you as far as derivation. The next one is the position equation, as it has to do with average velocity. And so we can kind of do a couple of things here. And we can say that, well, this is kind of based on distance equals rate times time. So we're actually going to assume that we have like a constant velocity. And as it turns out, we can replace this with the idea of displacement being average velocity times time. And so we can just substitute in our equation and then the equation for this. So I can say x minus x naught is displacement. Average velocity is the initial velocity plus the final velocity divided by 2, because you're taking the arithmetic mean there, and then that's times time. This is almost the same equation. If I add x naught to both sides, and really dividing something by 2 is the same as multiplying it by a half, so I'm kind of already there. But I want to show you one more thing. The other physics concept that we know from velocity versus time graphs is if I find the area under the graph, if it's a velocity versus time graph, that gets me the displacement. So area equals displacement. And so that just means that the displacement is equal to the area of this shape. Now this shape is a trapezoid. If you kind of turn your head to the sideways, sideways, you see like one base, here's the other base, and then here's the height. So we use the trapezoid formula, 1/2 the sum of the bases times the height. And so I can now substitute in the variables that I have in this graph for my trapezoid formula. So my displacement is equal to 1/2. We'll say the first base is this one, and so that is Vx naught. The second base is this one, that's Vx. And then the height is actually in our view of this, the width, and that's time. And so again, we have this equation popping out of what we know about graphs. So the relationships are all in there. The next video will go through the other two. There's a little bit more algebra for those, but they kind of work along the same lines.